All right. Hello, guys. So this is the loan due supplement from section 14.5, which is the chain rule, I believe. So in the chain rule section, we have introduced the so-called implicit function theorem, basically saying that if a function satisfies certain nice property, then its level set, where is it? Here. On its level set, you can locally solve one variable in terms of another one. So basically, say we're dealing with some curve, maybe like x squared plus y squared being 1, then under a nice condition, y can be locally solved as a function of x. In this particular case, it will be root of 1 minus x squared, plus or minus, depending on your location. So let us start the statement for this theorem, which I have already do it in 14.5, but just to jog your memories, and we will do the proof precisely. So let f be a continuously differentiable function, meaning that both the partial differentiation, fx and fy, are continuous, and it is supported on a domain D, belongs to a two-dimensional space. Suppose that for the point AB belongs to D, we have f of AB being 0, and that the partial derivative of f respect to y at the point AB is not 0. Then there is a small interval around the x-coordinate A. In this case, I write A minus epsilon, A plus epsilon, basically just a small interval around A, that you have a uniquely determined continuously differentiable function. Again, continuously differentiable function in this setting simply means that f prime is continuous. F here is a single variable function, okay? So the claim is that there is such function so that the following is justified. First of all, f satisfies this equation. Capital F of x will be 0. So basically, this point lies on the level set fxy being 0. And this term holds for every x belongs to this small interval. Secondly, that function is differentiable on that interval, and the derivative can be given by this formula. F prime of x is equal to minus capital Fx, plugging in the corresponding point, and capital Fy, plugging in the corresponding points for every x in that interval. Okay, so briefly saying is that whenever you're dealing with a level set or a level curve or level surfaces, then if the partial derivative respect to the variable that you're interested in is not 0, then that variable can be solved by the other variables. This is what we basically are saying. So let us dive into the proof. And just want to mention that the most important feature about this theorem is this guy, that we know how to differentiate the implicit function, implicitly defined function, basically. Oh, and yeah, maybe one more remark is that this is called implicit function because we don't really know what f looks like. It can be constructed, but the actual form is not really that obvious. For example, in this case, we have shown that y can be locally solved as x, right? And we actually gave a formula. However, if we're dealing with something like this, maybe more terms, then it is almost impossible to solve y in terms of x. So implicit function theorem does not tell us how the function looks like. That is why it is implicit. However, instead of knowing the function, we actually can derive the differentiation. And that is sufficiently enough for understanding the behavior of a function. Okay, so we'll break it into 3 steps. The first step is showing the existence and uniqueness of the function, f, little f. The second step is to show continuity of that particular function. And the third step is to show differentiability of that function. So, of course, differentiability implies continuity, so the second step might seem redundant, but actually when we are proving the differentiability, we require continuity. So that is why we split the steps into 3 different portions. All right, now let's start with the uniqueness and the existence. So first of all, we can obviously assume that FYAB is larger than 0. It is non-zero, right? So assuming it is strictly larger than 0 or strictly less than 0, it's of the same feature. So in this case, I assume that it's positive. I highly encourage you guys to try the negative one. It is a similar argument. So since Fy, this partial derivative, is continuous, we know that this is positive, meaning that locally it is positive. That is saying that Fy xy is always positive whenever x and y are close enough to the point AB. So in this box, b plus delta 1, b minus delta 1, a minus delta 1, a plus delta 1, you can choose such delta 1 so small so that because the positivity of fy at this point, fy is positive on this small box. Okay? Right. Secondly, because that f of AB is 0 by our definition, by the assumption of f of AB in this orange assumption, we know that again by the positivity of this derivative on this whole box that it is increasing along y, right? Because it is fy, xy is positive throughout this whole box. So if y increases, then the function also increases. In particular, this point has value 0. So we must have this point having value positive and this point having value negative, right? Okay, now we already understand that this is 0, function value 0. This function value is positive. This function value is negative. And now we apply again the continuity of f itself. So since the function value of this guy is negative, locally it will be negative, right, in this green box. And similarly, since this guy is positive, so locally, again, in a small box, maybe smaller than this box, is positive. So this whole guy here will be positive, and this whole guy here will be negative. Okay. So for now, based on the information of f of AB being 0 and fyab being positive, we can understand the function in this sense. First of all, this is 0. This guy whole, you can find a small delta 1 and possibly delta 2 so that this small box has positive function value. And this small box has negative function value. Okay? All right. And yeah, since oh yeah, this is what I just mentioned. So this is the precise statement. Whenever x and y are close enough to a, b plus delta 1, which is this point, in this green box, then you always have f of xy being positive. And the same thing happens for the lower box. In particular, as I mentioned, this line is negative and this line is positive. Okay? And we know that based on the intermediate value theorem, there will be, this is negative, right? The function value, and this is positive. So there will be indeed some point where you have a root, meaning that f will be 0, right? We're applying this function to this function, g of y equals to f of xy. So fix a particular x, then g of y is negative here, and g of y is positive here. So somewhere here will be 0, right? Okay, and that shows the existence of the function because we can construct that f of x by the particular root of that g of y. Okay, basically I'm saying that if we set this function, then f of x is some point so that you have g of f of x, which is f of x being 0. Okay, intermediate value theorem ensures that you have such point exists. However, why is it unique? Why is it not possible for, say, you have different options of 0 along a particular line? That is because the first assumption, which is fyxy is always positive on this box. So basically, we're saying that you're increasing from this negative value all the way to this positive value, okay? So that means that you cannot have two same points that share the same value because it is strictly positive. You're strictly increasing, right? So that ensures uniqueness. But maybe let me sort of go back. Intermediate value theorem ensures existence, and the fact that you're strictly increasing in terms of y tells you that you have uniqueness. So then we have constructed such f of x, which is in this green curve here, in this purple curve here, and it satisfies f of x to be 0. Okay, so now we have that little f, we can start and analyze the continuity and differentiability of that function. So first of all, for continuity, it's actually really simple. It's based on the previous argument. So you can see that this is almost the same picture as before. For any particular x naught belongs to this small interval, a minus delta 2, a plus delta 2. So that is, where is it? Okay, here. This small interval. Okay, I want to investigate the continuity of this function here. So for any of that particular point, we can always choose some delta. So we fix epsilon first. Don't forget that continuity is basically saying that for every given fixed epsilon, you can always find some delta so that f of x is close to f of x naught whenever x and x naught are close within the threshold of delta. So picking this x naught belongs to any particular point in this interval. We fix some delta 3 less than epsilon, which is possible to choose so that this whole guy here, again, yeah, this is basically the same thing. We can ensure that for some small delta, delta, I wrote delta 4 here, delta 4 here. So that, again, by the exactly same argument, since this guy has function value, capital F function value 0, right? So you can find somewhere here to be positive, somewhere here to be negative. And that is basically what we have done before, right? The same thing. But for now, we shrink the scale so that the delta 3 is given to be less than epsilon. And it's always possible because the smaller the box, the more property you can get from the box because locally you have more information. And therefore, yeah, again, the so-called uniquely determined f can be solved within this small region, right? And by definition, this purple line, f of x, is within delta 3 distance of f of x naught, right? As I mentioned here, f of x must lie between f of x naught minus delta 3 and f of x naught plus delta 3. So that basically means that f of x minus f of x naught is always less than delta 3, which is chosen to be less than epsilon whenever the x minus x naught is less than delta 4. So this is the corresponding associate threshold to epsilon. So since the epsilon here is actually arbitrary, we actually shows that the function f, it must be continuous. Okay? So it might be a little bit misleading by this diagram, but it is sort of the same thing here. We basically shrink down our diagram like this. This is what we have done in step 2. We investigate this small box and see that, okay, for a small epsilon threshold, you can perform the same type of argument. And under that threshold, the function value are not that different, at most by some epsilon. Okay, that is differentiability, and this is quite direct. Basically, everything regarding differentiability, differentiable derivative is about mean value theorem. So let us first go through this argument. We want to show that, again, for every x belongs to the domain, a minus delta 2, a plus delta 2, we always have f prime f of x, which is this guy, is given by minus fx divided by fy, evaluating on the corresponding point. So let us first look at some observation. What is capital F of x plus h f of x? So this guy is the same as this guy, right? That is because by definition, little f is such that f of x, little f of x is 0. And by applying mean value theorem to the first coordinate here, since we know that capital F is differentiable in the first coordinate, right? You have the partial derivative. So you have fx alpha for some value alpha between x. Oh, yeah, I already got here. Alpha is between x and x plus h. So that this difference can be represented by the gradient times the differences, right? So that is the mean value theorem, telling you that given a second line, you can always find some point where you have the same tangent line. So yeah, basically this gives us this for some alpha between x and x plus h. And then let us investigate this guy. Minus of capital F, x plus h, f of x, which is this guy, the minus of this guy. And again, this is the same thing as this guy, right? Because this guy is, again, 0 by definition of little f. And let us apply the MVT, mean value theorem, to the latter coordinate, because the first coordinate is the same, right? So it is will be the same thing as Fy, x plus h, beta, where beta is some value between f of x plus h and f of x here. And you have the differences between the y coordinates, x coordinate, y coordinate, I'm saying it correctly. So that is f of x plus h minus f of x. So both of these arguments come from the mean value theorem and the differentiability of f in the first and second coordinates. Okay, now combining these results, we can rewrite this different quotient as this formula. The numerator f of x plus h minus f of x given here can be written down by minus fx plus h f of x divided by this guy. So you have this guy. And don't forget that beta depends on h. Similarly, the h here can be evaluated by this guy divided by this guy, right? So you have this denominator. Yeah, by canceling the common term, you have minus fx alpha, f of x, fy, x plus h, beta. Now let us do some investigation on this alpha and beta. First of all, alpha is between x and x plus h, right? So when h goes to 0, alpha converges to x. And by the continuity of fx, the partial derivative, which we assume to be continuous, this guy also converges to fx x f of x whenever h goes to 0, right? So that is fine. The denominator is fine. The numerator is fine. For the denominator, this guy, beta is within f of x and f of x plus h, right? And since little f here, as we assume, is continuous, so that is why we prove continuity first. We now have f to be continuous, right? So when h goes to 0, f of x plus h also converges to f of x by continuity of little f. So that makes beta also converge to f of x, right? Because it is squeezed between f of x and f of x plus h. So beta will converge to f of x whenever h converges to 0. So taking h converge to 0, this guy converges to x, this guy obviously converges to x, this guy obviously converges to f of x. And by continuity of fx and fy, this whole thing will converge to this guy. And this whole thing will converge to this guy. So make sure you are really careful with the interplay between the input and output. Even if we know the input converges, the output might not converge. In this case, the input converges because basically this converges x by squeeze theorem. You have x and x plus h, right? And this also converges to f of x by squeeze theorem because this is convergent between these two guys, where this converges to f of x because of continuity. Lastly, the input converges and the output also converges because of the continuity assumed for fx and fy. Therefore, we see that f prime of x given by this different quotient taken limit is indeed what we assume, which is minus fx divided by fy, plugging in the corresponding point x f of x. So basically that's the proof of the implicit function theorem. You can generalize this to higher dimension. We can actually solve a higher dimensional function in terms of several variables instead of this one variable case. The proof is quite similar, but you'll have to have some knowledge on the linear algebra, and that's why I performed, in this case, a two-dimensional version. But it basically shows the essence of what we're actually doing. So locally, by intermediate value theorem, you can always find a point, and that point will be uniquely determined because of the positivity or negativity of your gradient. And based on that particular function, continuity is quite simple to solve. You can just shrink the argument smaller in step 1. And differentiability is quite direct using mean value theorem. So yeah, that's all. And I would say this is a really nice proof, and it shows that we can actually define function implicitly through a equation, where the equation has several nice properties, like having non-zero gradient. So yeah, that's all. And I will see you guys for the next supplement. See you.